Good afternoon, everyone, or good morning to you all. I would like to start by giving everyone Happy New Year and a prosperous New Year as well. And not lest I forget as well, Happy International Year of Quantum Science and Technology Year as well to all of you. We have about 3 minutes to start our lecture. Our facilitator is already online. And there are a couple of announcements. I'd like to start to give some of it now, and then at the end, I'll also give the rest. We have sent an email to all those who are in good standing for the survey for QIP, the Quantum in Pictures lectures. They need a survey on how the lectures went through. I'll urge all of you who are in good standing to do well to fill the survey, because they will also be given a certificate. They'll be awarded a certificate in respect of having to attend the lectures. So that is one of it as well. The other thing is that I hope each of you are checking your portal. We have a couple of lectures to have. This is just the first one for this new year. It will be left with 3 more for us to do. So kindly check your portal regularly and prepare accordingly. We will also have a number of quizzes and assignments to wrap up this year. That is the month of January, so that we can be done with this international school. So kindly gear up and get ready as we wrap up this international school for 2024. 2025 has a whole lot of package in store for us. At the right time, we'll be announcing them one after the other. So thank you very much and welcome once again to the International Year of Quantum Science and Technology.
Hi, everyone, and Happy New Year. Thank you, Henry, for giving an opportunity for us to present something here. We are really excited. And with me is Marina as well. And I'll let Marina first introduce herself, and then maybe I can go further.
Hey, everyone. Nice to meet everyone. And Happy New Year as well. So I'm just here to introduce myself today and talk a little bit about what we're going to see in the course, because today is just Bindiya's lecture. So before everything, I'll just send you the calendar, which today the idea of this course is to give you a general feeling of what we do in the field of quantum foundations. Through some topics that we picked, because this is the topics that we work on, and because we find them especially interesting, and we hope you'll see why we think that they're interesting. So in this first lecture, Bindiya is going to give you an introduction to quantum theory. So maybe some of it will be review, maybe some of it you will learn for the first time. And that's to prepare for the next 3 lectures. In the second lecture, which is on Monday, Ela and I, who are the 2 other instructors, we're going to talk to you about Bell's theorem via a more traditional way of talking about Bell's theorem. And then in the third lecture, I'm going to talk to you about causal inference, which is a framework to study causality that works that was developed in machine learning, so even not related to physics, and it has applications in many, many places, including in quantum physics. So I'm going to talk about this, and I'm going to relate this to Bell's theorem to say how this framework of causal inference can be applied to study quantum theory. And then in the final lecture, Ela is going to talk to you about the Wigner's friend thought experiment, which is maybe you've heard the term measurement problem of quantum theory, and this is it. So I think it's going to be very interesting. We're going to talk about foundational questions in quantum mechanics, really trying to understand what is quantum mechanics telling us about reality, which is something that physicists still don't know, or there's no consensus. Okay, so that's an introduction of what these 4 lectures are going to be. We're going to have one homework, one problem set that I'm going to send to you after lecture 2. And in the end, I'll probably make a survey asking what you thought as well. I just saw that Harry mentioned that the other course made a certificate. I didn't know this was a possibility. If you think that's fun, I can make a certificate for you too. But my word doesn't mean much, so I don't know how, official would this certificate be, but that sounds fun. Yeah, so, and finally, I'll just introduce myself. So my name is Marina. I'm from Brazil, and I'm now a PhD student in Perimeter Institute. Let me send you the link in case you want to take a look. Our team is all from Perimeter Institute. Both Ela and I, we are PhD students, and Bindiya is a teaching faculty at the Perimeter Institute in Canada. But the 3 of us all come from different places in the world. So it's cool. It's a very international place. Yeah, I think that's it. I'm in the 3rd year of my PhD, and I study quantum foundations. And now I think I'll leave it to Bindiya, who is going to also introduce herself and start her lecture. And I'll see you on Monday. Sorry, just one more thing. I'll also send my email here. If you have any question or anything you want to talk about, it can be about the course or just about life in academia. You can just send me an email. And that's it. Bye. See you on
Okay. Thank you, Marina. She is still there. Okay, so thanks a lot, Marina, for giving a brief overview of the course. I just jumped in. The course was planned by Marina and LA, and I just jumped in to give a review lecture, first lecture on quantum mechanics. And it won't be covering all the quantum mechanics, which is not possible for one lecture. But I'll just briefly describe only those concepts which would be used in the coming 3 lectures. So I'll try to keep it brief. And I don't know how many of you already are aware of the topics I'm going to cover, which would include the postulates of quantum mechanics, a little bit about what Bell states are. We don't go into detail, but that should be required for your homework problem. So I'll just tell what Bell states are and a little bit about the Bloch sphere, because that's very useful for the quantum information in itself. So I'm Bindiya, and as Marina said, I'm a part of the teaching team and administrative team here, and my research is related to atomic physics. I do some of the atomic physics calculations to support quantum technologies, and this is my website if you want to know more about my work. I had prepared lecture notes for the lecture so that you don't have to write those down and you just could concentrate on listening throughout the lecture. So Henry, I had emailed the lectures to you. Is it possible to send it to everyone?
Sure. We have a learning management system, so I'll put it on the platform, and then they will just go to the portal to download it.
Okay, so they are already with everyone.
Yes, I just saw it, so I'm going to just post it right away.
Okay, thank you so much. Thank you. So I'm trying to follow the notes so that there's least amount of confusion, and I'm going to start with the postulates of quantum mechanics. I'm assuming most of you might already know, but still I would go into the details, assuming that not many people are here aware. A number of people divide these postulates into 4 or 5 categories. I usually do it in 3 parts because some of the postulates are kind of related and are subpart of each other. But what these postulates actually mean. So quantum mechanics usually has earned a reputation of being very complicated, like it's very difficult to understand it. But when we are dealing with quantum mechanics mathematically, we make our life easier by giving a set of principles which kind of demonstrate how quantum mechanics work. So these principles, we don't have any proof for these principles, but these are the axioms on which the quantum mechanics is built on. So first postulate that any quantum mechanical book would describe would be the postulate of describing the state of the system. Postulate 1 says, and all of this is in the notes, but it says that in quantum mechanics, the physical state of a system at any instant of time, t, is specified by a ket vector psi. So the postulate in itself says that the physical state of a system at time t can be described by a vector, which in quantum mechanics we call as the ket vector, and we denote it in these brackets. The state itself is psi at time t, and these brackets are called the ket vectors. And these ket vectors, they belong to a space, which we also known as the Hilbert space. And they are also known as the ket space for these ket vectors. So ket space or Hilbert space. I'm sorry for my bad handwriting here. Now these vectors, since they could identify different physical states, we usually assign a identifier to them. For example, if my system consists of spin half systems, in that case, I can say that the ket space would consist of the upspins and the downspins of the system, and these states up and down would belong to a Hilbert space of spins, and the identifier I give here is S. Since I could be talking about more than one physical states, this identifier here tells me which system I'm talking about. Okay. Now, something similar in classical mechanics would be when we say that physical state of a system is specified by position and momentum. So in classical physics, state of the system is specified by the position x and its momentum p. In other words, if I have a classical object or classical system and I specify the position and momentum of that object at any instant of time, so this is time dependent, I kind of know everything about the system. So I know I would be able to calculate the state of the system at any other instant of time. The concept here is similar. So if I give you the ket state of the system in quantum systems, that would mean that I give you almost every information about the system. So this contains the information of the system in a similar way that these two parameters, they contain the information for classical systems. Okay, so there are a few comments I would like to make here. First is that when I'm describing the state of this system as psi, they usually have associated phases with them because in quantum mechanics, these phases, they appear as some complex coefficients, which I'm going to talk about a little later. But what's important here is that each of these state of the system, it can have an associated phase, which is written by E iota phi psi. And in quantum mechanics, these phases are not so important. These are called as the global phases, and they are not observed. We cannot observe them. So whatever observable I get from a state which has an associated phase phi, the same information I can get from the state without the phase phi. So in other words, this global phase has no physical significance in quantum mechanics. So this global phase has no physical significance. And by physical significance means that I cannot observe it, cannot be observed or measured. Okay. The second comment I would like to make here is that this ket space of vectors, which I said that this is the ket psi, like let's say if I have a system which has two possible states possible. For example, the spin case, there are two possible. Yeah.
Hello?
Yes, hello.
Please, did you say the global phase has no physical significance, meaning it cannot be observed or can?
It cannot be observed. Oh,
I
sorry.
think it
Cannot.
can.
Sorry. Yeah. It cannot be observed. So when you measure, then you don't have any information about the phase. The overall phase does not appear in the experimental measurements or observations. Thank you for pointing that out. Okay. So the second comment I would like to make is that if there are two possible or more than two possible states for a system, for example, for the case of spin, we had two possibilities, up spin and down spin. So let's say I have a system which has two possible states. It can be in psi 1 and psi 2. An important property of the Hilbert space to which these states belong, it says that the superposition of these two states, psi, would again be a state belonging to the same Hilbert space. So if psi 1 and psi 2, they belong to some Hilbert space H, then a superposition of these two states would also belong to the same Hilbert space. In other words, if I have upspin and downspin for an electron, then a linear combination of linear superposition of these up and down spins, the spin state signifying that superposition would also belong to that electron. And this superposition is different from the classical superposition because in quantum superposition, these coefficients they can be complex. Okay. The second comment I would like to make here is that for each ket vector psi, which belongs to Hilbert space H, there's a corresponding dual vector, which we call as the bra vector, and it belongs to a Hilbert space H star, which star is the complex conjugate of H space. So these are the ket vectors. And these are the bra vectors.
Hello?
Hello, yeah.
Yeah. So in this case, would the bra be in a dual space?
Yes.
Let's say Hilbert space, will it be a dual space where
Yes.
the ket vector will have its separate space and then the bra too?
Will have a separate space. That's correct.
Okay.
Okay.
But they are dual species though.
Yes. So
Okay.
each corresponding element here would have a corresponding element in this space.
Okay. Okay. Okay.
And maybe it's the right time to introduce something called the matrix representation for our ket and bra vectors. So in quantum mechanics, we usually, especially when we introduce quantum information, we use something called matrix representation for our vectors. And usually ket vectors, they are represented as a column matrix. And bra vectors, which are complex conjugate of these ket vectors, they are represented as row matrices. For example, let's come back to so throughout the lecture, I would use the example of our spin states because Marina and Ile are going to use that as their sample problem for describing their lectures. So for a spin half system, for example, an electron, usually we signify upspin as 0 ket state and downspin as 1 ket state. And sometimes the convention is used differently, but that's the standard convention. And this is a two-dimensional Hilbert space. By two-dimension, I mean that the spin system has only two possibilities when you do measurement. Either it'll appear in up or in down. And in matrix representation, these ket up and ket down are represented as a column matrix 1, 0 and 0, 1. And similarly, the bra representation for 0 is a row matrix, which is the transpose of these column matrices. Okay. And any general spin state can be written as a linear combination of these kets. With these complex coefficients A and B. And these complex coefficients A and B, they contain a very useful information. So they kind of give you the probabilities of the spin S being in 0 and being in 1, or the up and down. And we'll talk about these probabilities a little while. But alphas and betas, they are complex coefficients. And contain useful information about the probabilities. We'll talk about this a little later. Okay. Let's now talk about something called the inner product, because this is something we are going to use again. This is my comment 4. Inner product. So, for example, when you talk about any vectors, and these are kind of state vectors, for any vectors in your classical mechanics as well, you always talk about dot products, which when you take dot products for two vectors, A and B, let's say, it kind of gives you a number. The concept here is similar. The inner product of two ket vectors, it gives you a number, which could be a complex number. And the inner product is usually written in these brackets, round brackets, with a comma separating the two vectors. Between, you're taking the inner product. For example, the inner product between the state vector psi and let's say a phi would be written like this, and it's given as a bracket. So this inner product is known as the bra and a ket. And it's usually associated, it belongs to, this is a number and it could belong to the complex space. So it's not necessary that it's always a real number. Let's again go back to our spin example. Let's say we are taking a dot product for my up spin with a down spin state, which would mean, and when it comes to dot products, it's always useful to use the matrix notation. So remember, for 0, we had a column, we had a row matrix representation, 1, 0. And for 1, we had, for this ket vector, we had a row representation, which was 0, 1. And if I take a matrix multiplication of these two, it gives me 0. So it means that the inner product of 0 and 1 state is 0, which means that these states are orthogonal. And there are some states called as the normalized states. And by normalization, it would mean that the inner product of those states is 1. So if my state psi is normalized, then the inner product would be equal to 1. A number 1, yes. Okay. The next point is about the outer product. So similar to inner product, we also have something called outer product in quantum mechanics. Like the inner product, it gives you a number which belongs to the complex space. The outer product, on the other hand, is a kind of operator. And it is represented by a ket, product of ket and a bra. It's written as this. The notations are a ket and a bra. And this operator, when it acts on a state psi belonging to the Hilbert space of the psi states, it brings your state psi to phi, which belongs to Hilbert space phi. So it kind of changes the Hilbert space from one to the other. Let me show you by an example. So let's say if I operate this operator, and the operation of operators are always on the left-hand side. The operators, for example, this operator, when it acts on a state, in quantum mechanics, we write the operator on the left-hand side and the state on which it's acting on the right-hand side. So this operator, when it acts on a state psi prime, it kind of gives you, so this is the inner product for Hilbert space, inner product for the states belonging to Hilbert space H psi. It gives you a complex number. Let's say it gives you A. And what you're left with is a new state phi, which now belongs to Hilbert space H phi. Okay.
Question.
Yes.
Please, the inner product, is it that you're taking the inner product of the psi and then its complex conjugate
If
for the outer product?
for the outer product, these
Since
ones.
you've given a notation on the inner product with kind of like a hyphen there. And then most of the time, the notations for those ones are given as the complex conjugate, if I'm correct. For the outer product.
For the outer product or for the inner product?
For the outer product.
Okay.
I mean, no, the down part where the operator is acting on the inner product. You see that with the psi, there is another psi where you have like a quote on top.
Oh, okay. So
Is it?
these could belong to different states, but this is the ket vector belonging to Hilbert space H psi, and this could be the bra vector belonging to same Hilbert space, like the dual vector, but it will be complex conjugate, yes. But not necessarily they have the same state. So if I had written psi and psi, then it would have meant the complex conjugate of psi. By psi prime, I mean that it could be a different state.
Okay.
Yeah. But this would give you a complex number, because the inner product of any two states belonging to the same Hilbert space would give you a complex number.
Right.
Is that okay?
Yeah.
Okay.
So it's okay.
Yeah. The reason being that any state, like any state psi or psi prime, if they belong to the same Hilbert space H psi, then I can write these states in the eigenstates, in the same eigenstates for H psi, and we'll talk about eigenstates a little further. But I could represent, let's say, the eigenstates for H psi were 0 and 1. So I'm skipping some steps here, but I'm assuming you already know that. So let's say for a spin system, my eigenstates or eigenbases are 0 and 1. Then I could write these two different spin states as a linear superposition of 0 and 1. And when I take inner product of these two, I would always get a complex number. Okay.
Okay.
Yeah, thank you for that. Okay. Yeah. So in general, when an operator, which we usually signify as a hat on it, it operates on a system psi, it usually changes the system state to another state. For example, in this case, it's very nicely demonstrated that if the operator is the outer product of phi and psi, and it acts on some state psi, it actually changes the state of the system to phi. Okay. Now I'll make some small comment on the state vectors for our composite states, because they are going to be used when we describe the Bell's theorem. Composite states. So whatever we described for a single system, like a single spin or single atom or single electron. Composite states mean we are talking about 2 spins or 3 spins and so on. And a very commonly used terminology for quantum information especially is called the bipartite states. And bipartite state means 2 spin systems or 2 atom systems and so on. In quantum information, we usually call as like 2 qubits or something like that. 2 qubits or, yeah, I think that's the more common terminology, qubits, as the state or the quantum state of your system. So bipartite system means that we are talking about two states, two systems actually, 2 systems. And maybe I should write system here instead of state, bipartite system. And for example, earlier we were talking about a single spin S. Here I could say that instead of single spin S, which belongs to a Hilbert space, I'm talking about 2 different spins. Now they are entirely 2 different electrons. I'm not just talking about the state, 2 different states of 1 electron, but this is 1 electron and this is another electron. So there are 2 physically present systems, and this also belongs to Hilbert space S, which means that this electron could have a spin up or down, and this electron could also have a spin up and down. Now, when I am describing a system which is composite of these two electrons, the state of that system. So the state of a composite system, in this case, it's a bipart system. It consists of two electrons. It is given by the inner product of the states S1 and S2. Tensor product is given by of the subsystems of the states S1 and S2 of the subsystems. Let's understand that by an example. I think that makes things more clear. So let's say I have an electron. I have two electrons. So this is a bipartite system. And this electron is in, let's say, upspin. And this electron is in downspin. In that case, the combined state of the system, which let us write as let's write as S1 tensor product S2 would be given by 0, because the first electron is in upspin, 0, tensor product 1. And how do we take these tensor products? In matrix notation, it's really very simple. So in matrix notation, our 0 state was represented as 1, 0. And if I take a tensor product of this 1, 0 with one state, it's different from the simple matrix multiplication. In tensor product, what we do is we take product of the first element of your matrix here with the entire second matrix. And similarly for the second element multiplied by the entire second matrix, which gives you, instead of a, yeah.
Hello, I think the cat one in the
sorry.
bracket form supposed to be 0, 1. Yeah. Thank you.
Okay. 0, 1 and 0, 1. 0, 1 and 0, 0. So if you kind of see here, the dimension of my Hilbert space for composite states has increased. For my single system, the dimension of Hilbert space was 2, because my Hilbert space here had either upspin or downspin. But for a bipartite system, my possibilities have increased. And let's see how. For an electron in upspin, the entire basis would be either your system is in up or in down. But if you have a system of two electrons, then your possibilities are either the first one is in up and the other one is in up, or the first one is in up, the other is in down, or 1, 0 or 1, 1. See, the dimension has kind of here increased. Instead of these two, we have a 4-dimensional Hilbert space now. And my state of the bipartite system, which is given by S1 and S2, would be now linear combination of any of these 4 possibilities. And each of these is represented by a 4x1 matrix. I hope this is clear. This is the end of our first postulate and a bit of discussion. Are there any questions or comments related to this? Maybe I can also mention that these tensor products between these states, sometimes we choose not to write them, and this notation is equivalent to this notation, which is equivalent to this notation. So just to save time, we use these three notations interchangeably.
Please a bit so that I check something.
Yeah, sorry, can you repeat? Your voice was breaking.
Please go up a bit so that I check something.
Okay. Is the speed of the lecture okay? Or
Oh no, stop.
I'm sorry?
I want to see where you wrote the composite, the tensor product, the
Yes.
beginning, where you
I'm really sorry. I can't. There's a lot of voice breaking. Is it only for me? Can you write it in the chat window?
Yeah, hello.
Yes.
Yeah, I think he has a network problem, but I have a question too.
Okay.
Yeah, so it means that when we have that 01 will give us 0100, right?
Yes.
And then so that 00 will be 0000.
No. So 00 would give us, maybe I can write it,
Okay.
would give us all the possibilities. For example, here we wrote as 1 and 0, and this as 0 and 1, which kind of signifies that the spin is in up and spin is in down. For the four-dimensional Hilbert space for two bipartite systems, 00 would mean both are in up, or 01 would mean one is in up, the first one is in up, and 1, 0 would mean this, and similarly 1, 1 would mean
Yeah, all right. Thank you. That's what I was looking for. Okay.
it's kind of the binary system, if you are aware of the
Yeah.
binary system. And it's really
Yeah.
simple. You don't even have to take the tensor product most of the time. For example, if instead of a bipartite system, I had a tripartite system, I don't know how it says, but I had 3 spins. 00 would be very easy, and I could just write it as 1. And since now the dimension would increase to 2 to 8 possibilities, I would have 1 and then 7 zeros here. 1, 2, 3, 4, 5, 6, 7, 8. This would be my tensor product for these 3 systems.
Okay, I got it now. Thank you.
Okay. Are there any other questions?
hello. Please, I learned that the tensor product is a fancy way of saying an entanglement. Is that the case here?
Yes, we need, I wouldn't say exactly that, but yes, entangled systems cannot be written as tensor product of 2 separate subsystems. And thank you for bringing this up. We'll talk about entanglement when we talk about Bell states. And we see that tensor product can kind of help us in finding if the system is entangled or not. And since for entangled system, we should at least have 2 subsystems, we need this representation for composite systems in that case. Thank you for bringing this up.
You're welcome.
Okay. I saw there was another hand raise. And I think this tensor product might be new for some of you. Postulates you have already seen. So this part is not included in my notes, but maybe it's interesting to note that we could also take tensor product of operators. For example, if I have an operator A, let's say this polyspin matrices, so sigma x, which is an operator. I think poly x is given by this. And there's a spin matrix sigma z. And poly for sigma z, can anyone remind me what's the poly for sigma z? It's 0, 1, -1? I think so. Oh, sorry, no. Sorry. Should be, I think 0, 1 -1, 0. I think so. But I could also take a tensor product of these operators as well. And the idea, again, remains same. So I take product of this element with the entire matrix here. And product of this element with the entire matrix. So instead of my 4x4 matrix, which was the spin operator, which could act on the upspin or downspin, like this. Now this poly operator is going to act on the bipartite spin system. So it would maybe, let's say, act on 0-0 system. So in other words, what I want to say is that if I'm talking about bipartite systems, which consist of two different subsystems, like tensor product of two different subsystems, then the operators, the dimension of the operators also increase. So this was the operator for my single spin S. If I take tensor product of these operators would correspond to my bipartite system S1 tensor product S2. Okay. Can we now discuss the second postulate?
Yes.
Okay, so let's now talk about postulate 2. Postulate 2 says that every physical observable let's say we write it by A, corresponds to a Hermitian operator A hat, and these operators are always written with a hat on them, whose eigenvectors form a complete basis. So this actually postulate is broken into two parts. This is the first part of the second postulate, and we'll talk about the second part when we discuss measurement. But what this postulate says that in quantum mechanics, I can operate something on my state, and that state of the system, it changes. That's what we saw earlier. Now, if I want an operator corresponding to some observable, like all the operators in quantum mechanics, they don't corresponding to physical observable. And what do we mean by physical observable is something which we can experimentally measure. For example, momentum or energy of the system is experimentally measurable. So if I have a physical observable, A, let's say momentum, then with that physical observable, there would be always a corresponding Hermitian operator. And the eigenvectors of those Hermitian operators, remember we wrote these operators as matrices, so they would have some eigenvectors and eigenvalues. So these eigenvectors for these Hermitian operators, they always form a complete basis. And what we mean by complete basis is that a system would be able to represent in terms of these bases. I can give an example to make things more clear here. But in classical mechanics, these observables, they are usually functions of our x and p's. For example, in classical mechanics, kinetic energy is an observable, which is a function of momentum p squared by 2m. Similarly, in quantum mechanics, if I have an observable, let's say momentum is an observable, then it will have an associated operator, and we write that operator with a hat on the momentum p, and this operator would always be Hermitian. And since it's Hermitian, the eigenvectors of p would form a complete basis. And eigenvalues, since this is an observable quantity, when I observe it, I should always get a real value, and the observed values are nothing but the eigenvalues. Eigenvalue of p are always real. Maybe momentum was not a very good example. We should stick to our spin example here. And spins are observable, like I can do measurement and check if my system is in upspin or downspin. So one good example here would be, that's also given in the notes. Yep. So one good example would be, let's say we talk about the operator polyspin x, poly operator sigma x. So now this corresponds to an operator which gives us, when we operate this on a system, it gives us the spin values in x direction of the system, okay? In the, yeah, so this is kind of an observable. So associated with this observable are these operators, polyspin operators, and maybe we should also write on hat. Through the lecture notes, and maybe today in the lecture, I sometimes miss this hat, but when I talk about observable or operators, they are kind of interchangeable. They kind of mean same, okay? So corresponding to a spin in x direction, which is an observable, I can measure it. There's a corresponding operator, which we call as the poly x operator or the polyspin operator sigma x. And this poly x operator has a form which we earlier wrote as 0, 1, 1, 0. And as you can see, this is a Hermitian operator. So this is Hermitian. And if I find the eigenvectors and eigenvalues for this Hermitian operators, my eigenvalues would be either +1 or -1. And my eigenvectors would be so eigenvectors are written as either plus corresponding to the eigenvalue 1, which are 0, +1. And the other eigenvector corresponding to the eigenvalue -1 would be 0, -1. And in matrix form, if you're more comfortable with that, this would just mean 1/√2, 1, 1. And this would means 1 over root 2, 1 minus 1. So these are the eigenvectors for our Pauli spin matrix sigma x, and these are the eigenvalues. These eigenvalues are real, and these eigenvectors, they form a basis for my spin, which means that if I want to write any state for my spin in x direction, I would be able to write it as a linear superposition of plus and minus. So any state would be, I just need to change the coefficients, these probabilities, and I can represent any spin state in x direction as a linear combination of plus and minus. Okay. Is this postulate clear? Or if there are any questions? Okay, that's nice. So in continuation with this postulate, there is a B part of this postulate, which talks about measurement. Now, as we said, that there are operators corresponding to observable, and observables are quantities which we get when we do measurement on our system. The second postulate says that the eigenvalues of A are the possible outcomes of the measurement and the probability of finding outcome, some outcome, let's say AN, is given by Bond's rule. So this is a very important rule, which kind of tells you that when we do measurement on a system, what is the probability of getting a particular answer? So probability of getting an outcome AN is, and I'll describe what this AN actually means in a while, and also describe what the CN means. Okay, where psi is the state of the system, and AN is the eigenvector, with the S corresponding to eigenvalue AN. Okay.
Hello.
Yeah.
Please, if I get you well, are you trying to say that the eigenvalues are probabilities, or if you can come clearer for me?
No, eigenvalues are not the probabilities.
All right.
Yeah, the coefficient. Okay, let me give an example and then describe what the eigenvalues and the CN. The CN are the probabilities. They give the coefficients, they give the idea of the probability. So it's like this. When you do a measurement on a system, what you get as a result is one of the eigenvalues. For example, if I have an electron, it's either in up or a down spin. When I do measurement on that electron, what result I would get is one of the eigenvalues, which is either plus half or minus half, which describes either it's in up spin or down spin. But the probability of getting plus half and minus half is something different, which is associated with these coefficients CN. So let's understand this by an example, okay? So as I earlier said, that these operators, when they act on some state, They change the state of the system, right? Remember that? Now, there are special states corresponding to an operator when that operator acts on these special states, which I'm writing as AN. The state of the system, it does not change. It remains same. What you have is only a number associated corresponding to that state. And these states are called the eigenstates of the system, which don't change when you operate an operator on them. Eigenstates. And these coefficients here, these numbers here, are called the eigenvalues corresponding to these eigenstates. For example, if I have a spin X system and I operate sigma X, which is the Pauli spin operator corresponding to the X direction, what I'll always get is either plus half or minus half. And my spin state won't change. It will remain as Sx always. Okay. So this Sx could be, I could say it could be 0, which is upspin in X direction. It would give me h/2. And the spin would still remain up in X direction. Or sigma X, when it acts on 1, which is the downspin in X direction, it would give me minus h/2, which is the eigenvalue corresponding to the downspin, and the spin of the system won't change. So that means this state is an eigenstate for my operator sigma X, and these are the eigenvalues corresponding to it. Okay. And that's not always true. For example, if I operated sigma Z on my Sx, then my state would change. It won't remain Sx. Okay, it would change. This would be, I think, this would be one of these sigma Z states, like the eigenstates corresponding to the Pauli spin operator Z. Okay, maybe we can do an example here. I don't know what here should be, but this would definitely give a state which would be different from the state Sx, since this state is not the eigenstate for my operator sigma Z. So it will be a different state. Okay, is this thing clear?
Yes.
Okay,
Yes,
great.
please.
All right. So moving forward, this is clear that this eigenvalue, which we also term as this equation, we say as the eigenvalue equation. It says that if An is the eigenstate corresponding to my operator A, and I operate A on this special eigenstate, my state does not change. There's only a coefficient, which is the eigenvalue, which is attached to it now. My second postulate says that when I make measurement on any system, the possible outcomes would be one of the eigenvalues of these operator A. For example, again, coming back to this spin example, let's say my spin X was in superposition of the up and the down, okay? So this was my superposition state. And now I do a measurement on my system, and measurement here would mean that maybe I should introduce the measurement first here. But when I do measurement on my system, what I'll observe is either I will see my system in upspin or in downspin. These are the two possible outcomes I would get. Whenever I do measurement on my spin system, the observable would be either upspin, eigenvalue h×2, or downspin, eigenvalue minus h/2. This is what I'm going to observe. And the probability that I observe my system in upspin is given by this alpha, And it's written as P, probability of getting alpha would be the inner product of 0 with Sx and squared, which is nothing but this coefficient squared. And probability of getting downspin or the eigenvalue minus h cross half in my experiments would be this is modulus square of the system. Okay, so these are the probabilities with which I'm going to get the answer, but the observable itself would be either plus h cross by 2 or minus h cross by 2, which signify that I see the system in upspin, and this means that I see the system in downspin. Is this thing clear? The difference between the p's, which are given by these complex coefficient alphas, and the eigenvalues, which are the observable itself, which are these quantities. Okay. Any questions before we go to measurement part?
Hello.
Yes.
So it means the sum of the two probabilities will give us 1,
Yes.
since it is either up or down.
Yes. Exactly. Yes. That's something which we are also going to discuss when we do measurement, but maybe it's a good place to bring it here that these probabilities, the sum of probabilities of all the options. So here the options were only up or down spin. Let's say if I had a system where there were 3 possibilities allowed, 0, 1, and 2. In that case, the sum of probability of 0 plus sum of probability of 1 and sum of probability of 2, all these sums would be 1. So sum of probabilities of all the options available would always be 1. In this case, the alpha squared plus beta squared is always equal to 1. Okay. So let's talk about some example of measurements. So measurement can be described in a number of ways. And maybe after describing this measurement, we can take a 10-minute break and then discuss the third postulate, which is the last postulate. Okay, so measurement can be described in a number of ways. And one of the ways to describe measurement is using something called projection operators. And in my notes, I write it as AN. And these projection operators are outer product of ANs. And remember, these ANs are the eigenvectors of my operator A. Okay. So for these measurements, these special measurements are called projective measurements. Projective measurements. They consist of the entire set of my AN, all the projections that are possible, and they satisfy the completeness relation, which means this, that sum of all the possible projections would be equal to I. For the case of spin system, my projection operators would either be the outer product of 0, which I can write as A0, or outer product of 1. So these are the projections, projection for 1 and projection for 0. Okay. And the complete set consists only of A0 and A1 because there is no other possibility for spin half system. That's the complete set. And sum of the all possibilities. So maybe I should write this plus this is equal to 1. Because there's no other possibility of in my spin half system. I could either find my system in 0 or in 1. So kind of these projection operators tell you the probability of finding your system in 0 or probability of finding the system in 1. It's like how much contribution your state has from 0. That's the information your projective operator A0 is going to give. And how much contribution your state has from 1 is the information which A1 gives. For example, let's say if I have a spin system which is only in up state, or maybe let's take a generic example. It's in a superposition of up and down. Okay, so this is my spin state. If I take a projective, like if I take a projection of A0 on S, it would tell me that what part of S was composed of 0, which is in this case like 1 by root 2 only. So let's see what it gives. So if I operate 0 on 1 on my state S, so this would give me 0 plus. So this operator acting on 0 would give me this term here. And this operator, projection operator, acting on 1 would give me. And we know that this is a normalized state. So this is 1. And this is orthogonal. So this is 0. And what we get in the end is by root. And that's true. If you look at this state, this part of your state is the contribution from 0. That's the answer which you get from here. So it's kind of similar to the vector projection. Like if you have a vector and you take a projection by taking inner product, you kind of get information how much contribution from that vector is coming, right? That kind of projection, a kind of shadow on that vector. But is this clear what we mean by projection operators? And projective measurement are kind of some of all the possibilities of projection operators, and they form a completeness, all these projection operators. And if I have a state psi, then the probability that I would get n as an answer, probability of outcome n after doing this projective measurement would be, so probability of finding n would be given by which is actually nothing but equal to this for case of our projective measurements. Okay. So for our projective measurements, an is always equal to an dagger an. That's a special case of measurements we have. And the state update after I do measurement is, so the state would be that I operated my projection operator on psi, I get a new state, and then divided by this probability to normalize it. So this is my new state, which I'll get after I do projective measurement on my system. Okay, we'll understand this by an example. Okay, let's say let's say, coming back to our spin example, say I have A0 as the projection operator for 0 state. And if psi is given by alpha 0 plus beta 1, then my state update, the new state which I get after I do this projective measurement on my state psi would be, so the new state, let's write it at psi 0, maybe psi 0 prime, psi prime, would be A0 acting on psi. Not just that, I also have to divide it by under root of Pn. Let's calculate it for this example. My Pn, which is a probability, in this case, since I'm talking about 0, maybe I should write P0 here. Probability of getting 0, okay? So probability of getting 0 is given by this matrix here. Be psi A0 dagger A0 psi. This is my probability. And A0 dagger is a Hermitian operator here. So if I take Hermitian conjugate of this operator, it would again give me the same state. If I substitute these two in here, this is 1, and this here is, if you remember, nothing but my coefficient yeah, these are the probabilities, and this gives me the coefficient A alpha star and alpha. So this is alpha star. We did it in some of our steps previously. This is my coefficient A, and this is my coefficient A star, the conjugate of it. So this P0 is given by the probability. This probability is given by the coefficient alphas, which are attached to my state here. So my state update in this case would be nothing but 0, 0 acting on my state psi, which is alpha 0 plus beta 1, divided by this under root of probability, which is under root of alpha squared. And what I get in the end is alpha. So this would give me 1, alpha 0, and this would give me, yeah. So this would be my state update. My new state, after I do measurement, a projective measurement this on my state, would give me a new state, which would be alpha 0 divided by alpha. Is this thing clear? Maybe I can summarize it to make things more clear. Would that help? Does anyone want me to summarize what we did with the measurement here, or everything is okay?
I think we are fine.
This is fine? Okay, that's good. Any other questions? This was our end of postulate 2. Postulate 3 is something which we'll quickly go over because that's something which doesn't require any kind of mathematical understanding. It's just conceptual and not too long. Before we move ahead, are there any questions related to postulate 1 and postulate 2? And in the end, we are going to summarize everything with what we did. Okay, if not, then let's come to postulate 3. Postulate 3 is something which I'm assuming you would all be familiar with. It kind of gives you the time evolution of your system. So whatever we talked before was associated with a state psi at any instant of time t. So we didn't kind of mention that this psi is time dependent in whatever discussion we did previously, because we were talking about one particular instant of time at one time, and time was not moving, or we were not studying the time dynamics of the system. But postulate 3 kind of gives you the information of how the time evolution of your state takes place. And that's why we kind of associate a time t with its state psi. So instead of just writing it as a ket vector psi, we are now going to write it as ket vector psi, which is dependent on t. So postulate 3 gives the time evolution, gives you time evolution of your state psi at time t. And it says that this time evolution is governed by Schrodinger's equation. And this Schrodinger equation is nothing but a unitary transformation. So let me first write this Schrodinger equation. I h bar. So derivative of your state, time derivative of your state at psi t gives you an observable energy, or the Hamiltonian of your system, operating on your system psi. So this is what Schrodinger equation actually tells, that the operator corresponding to the energy of the system operating on your system at any time t is equivalent to taking time derivative of your psi. That's why it's a time evolution, because you're kind of studying the time evolution, how your state changes with time is governed by this Hamiltonian of the system. So it's something like in classical mechanics, you apply a force and your system moves. The system, like you apply a potential or a force, maybe potential is a better term to use. So you apply a potential on your system, and that's how your system propagates in time. The concept here is very similar. In quantum mechanics, it's the Hamiltonian of the system, which is kind of giving you the information. So this has the information about the kinetic energy of the system and also the potential energy of the system. So this kind of gives you what kind of environment or what kind of energy the system is in, and that energy, it kind of governs the dynamic of the system, how the system is going to evolve, how the states are going to change over a period of time. That's what Schrodinger equation tells us. And this Schrodinger equation, which for most of you is very familiar, is equivalent to saying that this transformation of the system, so my psi state at any time t is governed by a unitary transformation ut0 psi t0. Both these equations are equivalent, okay? What does this equation tell me? This equation tells me, again, something similar to what Schrodinger equation tells me, but this says that if I know the state of my system at an earlier time t0, so t is greater than t0 here. So if I know what was my state of the system at t0, I can calculate the state of my system at t by using this unitary operator. And there's a reason why we call it as unitary, which I'll discuss, unitary operator. And since these two are equivalent, H and U, they are related. And both are operators, actually. And maybe you have seen this relation before, but the relation between H and T is as follows. U T T0 is equal to exponential minus iota H by T, H by H bar, t minus t0. So this is a relation between u and t. Since they're both giving the same information, this equation is also telling me how my psi changes with time. And this equation also tells me that if I know the state psi at some previous time, I can calculate it at a later time t. Okay. Now this is a unitary operator, and this t and t0 here just means that this unitary operator is evolving my system from t0 to t. Okay. Now some important properties of this unitary operator. Why we call it as unitary firstly? So unitary operator have a very important property which says that unitary operation, they preserve norm. Preserve normalization. Normalization. What does this mean? That if I start, if let's say at t0, my state of the system was psi t0, this was my ket state representing system. Let's say it was in upspin at time 0. And I evolve my system using some unitary u, which takes my spin at t0 to spin at some other time t. Now it could have changed, maybe changed to upspin or downspin or spin in z direction or something. But there has been an evolution in the system. The state of the system changes, and it changes to this state. The new state which I get from here, let's say it's psi t. Unitary operation says that if I started with a normalized state, normalized, which means that if this, remember normalization was given by this inner product as 1. If I started with a normalized state psi t0, apply a unitary operation on it, then the new state which I get will always be normalized. So it does not change its norm. Psi t would always be normalized. These are unitary operations. They preserve norm, which means that they are kind of not interacting with the environment. They are kind of closed. Because if they're interacting with the environment, they'll always decay and they'll lose their normalization. Like they'll communicate with the environment. But this is something, a concept used in quantum information. I won't like to go into details, but I'll be happy to talk if somebody is interested in all these advanced topics. But this is what unitary operation means, that your state, if you start with a normalized state, you will not lose your normalization. Your state would remain normalized. In case of non-unitary operation, your normalization, it decays and your state is lost. Like sometimes you get no information in the end. Okay. This was one important property for unitary operations, that they preserve norm. The other property is called the composition property. So composition property says that let's say I'm interested in finding how my system evolves from time t0 to t2. Then I can write this time evolution as a product of evolution of system from t0 to some intermediate time t1, and then from t1 to t2. This is what composition says. So if I am moving my system from t0 to, let's say, t2, then I could first evolve it to t1, calculate psi here, then psi here, and then apply unitary here to calculate psi at the final time t2. This is what composition property says. And as a consequence of this composition property, if I'm looking at the time evolution, and let's say I do not evolve my system. So my unitary is that I do not evolve. I'm calculating system at T0 and I'm not evolving, I'm again seeing it at T0, this would always be equal to doing nothing on my system. So this is an identity operator. This means I did nothing to my system. I didn't evolve it. Also, there's something called inversion. And this inversion property has many deep meaning. It kind of brings a question about the arrow of your time, like which direction your time is involving in. This is a very good fundamental question. But let's not go into detail, but the inversion property says that evolving my system from T0 to T1. So evolving from T0 to T1 is equivalent to the inverse of evolving my system from T1 to T0. So this evolution is equal to the inverse of this evolution. That's what the inversion property says. So U of T1, T0 is equal to U inverse of T0, T1. It kind of is very obvious from this identity operation. So if I break in here, let's say, I can write this as U of T0, T1, U of T1, T0 is equal to identity. You can use the composition property here, which would mean that U of, now if I take inverse of U on both sides, so if I take U inverse T0, T1, U of T0, T1 is equal to, this is nothing but your identity. So what you get is this inversion property, which I wrote here. Okay. Any questions? This is the end of our postulates in quantum mechanics. And what information these postulates, they give us, that the first postulate, it tells us how to describe my system. It tells us that we always associate a ket state, which gives me the information about my system. And corresponding to a ket state, there's always a bra state, which is a kind of conjugate of the system. And I can calculate inner product and outer products in these spaces. I can also write the composition of systems by taking tensor products of these ket space. Postulate 2 gives us very important information about the observables and operators. It says that every physical observable, which is measurable, they can be represented as Hermitian operator. So the eigenvectors for these Hermitian operators, they form a complete basis, which means that any state of the system I can write as a superposition of these eigenstates. And the eigenvalues of these Hermitian operators, they are always real. And whenever I do measurement on my system or I observe a system, I get one of these eigenvalues as my result with a probability which is attached to the coefficients of the state of the system. And the third postulate, it gives me very important information about the time evolution of my system. For Marina's lecture, when we talked about measurement and we updated the system, I think that would be a very useful exercise to do. That when we update a system, we are not just applying the operator on the system, we are also dividing it by the square root of the probabilities, because that's required to normalize our system. Otherwise, you won't get any normalized outcome. Are these points clear to everyone before we start with the new topic of Bell state? Or are there any questions? Okay, so I'm assuming that there are no questions, and we can talk about now the entangled belt states, okay? So entangled states are kind of a bipartite system. But they are different from the bipartite systems which we discussed earlier, which we wrote as the tensor product of two subsystems. Remember, when we discussed bipartite system, we said that the state of my bipartite system can be written as tensor product of the subsystems. For entangled state, that's not possible. So let's write our entangled state as, let me write as at phi. So if phi is an entangled state, then I cannot write it as a tensor product of two separable states. For example, one of the very good examples for an entangled state is the Bell state, phi plus, which is given by 1 over square root 2. This is something we need for normalization of the state, given by the fact that the first spin is in upspin, second is in upspin, or the first is in downspin and the second is in downspin. That's all. You cannot write this state as a tensor product of two separate states. This is a perfect example of an entangled state. So the actual meaning of entanglement is that that two separate states can never describe the complete system, and the state which is actually describing the system is being shared by the subsystems. So both the electrons, they are kind of sharing the same state, and you cannot write that state as separately consisting of the subsystems of the two entangled pairs. Maybe I can demonstrate this by an example. Let's say if the system was not entangled, I started with a spin state psi 1, which was in either in spin 1 or in spin. So it was in superposition of up and down spin. And similarly, for psi 2, if I started with an up and down spin, superposition of up and down. So I have separate states describing my both systems. And if I now write a bipartite state of this system, so another way of doing tensor product in terms of these state gets, the earlier we showed was in terms of matrices. For tensor product, this for the state representation, state vector representation, if I'm taking these tensor product, it's just normally as any product, in which case, so this would be 1 by 2, and this would be multiplied by both these quantities, kind of distributive. Zero, 1, plus 1, 0, and 1, 1. So this is multiplied by both, and this is also, these is also multiplied by both. I get 4 of these terms here. Now this state is not entangled state. Why? Because this state is a product of tensor product of two separable states. I can describe one electron using this state and the other electron using this state. So this is not an entangled state. However, for states like these, I can never write it as product of two separate states. So I always use this complete wave function or the state vector to describe my complete system. They kind of share the same state. Both the electrons, they share the same state, phi plus. Is this thing very clear? Like, this is something very conceptual. and very important. In other words, when I'm saying that they share the same wave function or wave state vector, it means that if I'm doing something with one of the electrons here, and since both these electrons, they share the same state, this something automatically going to happen to the second electron. You cannot help it. You cannot control the operation just on one of these states. You cannot do that. If you do a measurement on this, this is automatically going to get affected because they are now represented by single state. In this case, it was not like you could have just done measurement on one of your states and it would have not affected the other one. Is this thing clear? And this is something which needs more of discussion, and I'm happy to discuss it more.
It's okay to me.
Okay, good. Now, there are 4 different kinds of Bell states which are given in my notes. I will not write, like, maybe I can just write it quickly here. These Bell states are called maximally entangled. So entanglement is actually not a black or white thing. It's not like zero entanglement and entanglement. It's kind of a spectrum. So you could have zero entanglement and you can increase the entanglement to a maximally entangled state. And Bell states, they are kind of maximally entangled. And there are 4 kind of Bell states, psi plus minus, which is 1 over root 2. And phi plus minus. Some very important properties for Bell states is that they are maximally entangled, they are non-separable, and they form an orthogonal basis, which means that if I take inner product among these Bell states, if I take inner product of psi plus with, let's say, phi plus, this would always give me 0. And if I take inner product of psi plus with itself, it would give me 1. And that's true for any of the combinations here. So they form an orthogonal basis. I can represent any entangled state in terms of these Bell states. And some key features are that if I measure a property like a spin or polarization of one of the entangled particles, since this share the same state, the result of this measurement, it affects the property of the other particle. And when I'm saying affects the property of the other particle, I don't mean that there's a communication faster than speed of light between the 2 states. That's not true. This is a quantum correlation which is not happening at light, like this communication is not happening at speed greater than the speed of light, because that's some misconception which prevails in sciences. Okay. So both the particles are actually not communicating. It's just that they share the same state. So if you do something with one, the other has to get affected. Okay, this is the end of Bell's state. And this is only part which you are going to require for your homework problem. And I'm not going into details of this. Entanglement is a very beautiful topic, which can be discussed very fundamentally as well. But let's leave it here. And the third topic which Marina and Ele are going to talk about are the Bloch spheres. Any questions here with the postulates or with the Bell states or with the entanglement? Okay, good. So Bloch sphere is a kind of a geometrical representation to represent any quantum system which is two-leveled. And so far we have always discussed a spin system, which is actually a two-leveled system. The only possibility is up or down spin. It's a very beautiful geometric representation. Geometrical representation of a two-level quantum system. So the two-level system could have two bases. Let's signify these bases by 0. Let's write these bases by 0 and 1. And your two-level system, which I'm going to also sometimes refer to as a qubit. This two-level system would be in superposition. Let's write it as qubit. The state of this qubit would be in superposition of these two bases, 0 and 1. And these alphas here are the probabilities and can be complex conjugate, and these would be always equal to 1. The sum of these probabilities would be sum. This spin is a very good example where we can say that either the qubit system is in upspin or in downspin with some probability attached to it, alphas and betas. Now, in terms of this spin, the geometrical representation is given by this Bloch sphere. And we have the z-axis attached to it, the x and the y-axis. And any spin or any qubit two-level system can be represented on the surface of this Bloch sphere. For example, this could represent a two-level quantum system. Let's write it as psi. Now let's define the axis of this Bloch sphere. So the z-axis here, let's just talk about spin systems, okay? Let's say this Bloch sphere is representing a spin system. In that case, the z-axis here is going to give me the spin in the z direction or the z direction. So the north pole here, it gives me the upspin state. Let's write it as 0. And the south pole, the negative z direction, it gives me the downspin. Okay. And any general spin state in z direction would be a linear superposition of this up and down. And it would be represented as, so any linear superposition would be anywhere on this sphere. It would be represented as S of Z. Okay. Additionally, I could also calculate, I could also show what would be on the Z and the on the X and the Y axis. So it turns out that these eigenstates on the Z axis, they are actually the eigenstates. So the 0 and 1 are eigenstates of my poly Z matrix. For spin in X direction, S of X, the state is again a linear combination of my eigenstates plus and minus. And remember, we calculated these eigenstates plus and minus for Sx, they were eigenstates of sigma x and were written as plus was written as 0 plus 1 by root 2. And 0 and 1 are the eigenstates of your Sz. And minus was written as, we saw that earlier, that these are the eigenstates for my polyspin sigma x. So x positive gives me the spin, up spin in x direction, and the negative x direction here, it gives me the polyspin, spin in the x direction with a down eigenvalue. So this is minus state and this is plus state. And again, these are superpositions of my zeros and ones. And similarly for spin in y direction, this state is superposition of the eigenstates for my sigma y, which are written as I and minus I. So these two are eigenstates of my polyspin sigma y, and I is actually, I think it's 0 plus I1 by root 2, and minus I is similarly 0 minus I1 by root 2. So positive y gives a state corresponding to I, and exactly opposite to positive y, which is negative y, gives you the eigenstate minus eta. Okay. And what's also important here is that the states which are exactly opposite to each other are orthogonal, which means that 0 and 1 would be, the inner product of 0 and 1 would be 0. Inner product of plus and minus would be 0. And similarly, inner product of this would be 0. But if I take inner product of these two states, then it won't be 0. So for example, if I take inner product of 0 and some other state on the Bloch sphere, let's say I choose plus, then it would be, this I write it as 0 plus 1 by root 2. So it's actually 1 by root 2. This would give me 1. And this inner product would give me 0. So this inner product is not 0. But any two states on the Bloch sphere, let's say this state and this state orthogonal, like exactly opposite to each other, they, when I take inner product of them, they would always be equal to 0. The last thing which I want to do here is to show that we can actually represent these Bloch sphere in terms of the spherical polar coordinates. And for that, let's first write how we represent the superposed states on a Bloch sphere, okay? So superposition on Bloch sphere. So we said that the superposition on Bloch sphere is written as alpha 0, beta 1, and these coefficients alphas and betas are complex coefficients with their probabilities 1. So one very general ansatz, which you might have seen in your complex number theory, for alpha and beta are to represent them in terms of sine and cosine. So I can write alpha as cos of gamma exponential iota delta, and beta as sine of gamma exponential iota, let's say eta. So this ansatz, as you can see, it satisfies both our conditions. First, that alpha and beta, they are complex. Yes, they are complex. And also the squared sum of these alphas and betas is equal to 1. So this is a very good ansatz which satisfies both the conditions. So if I start with this ansatz and substitute it in my psi, I can write my psi as a function of gamma. Sorry, let's just write psi. My psi would be cos of gamma ei delta 0 plus sine of gamma ei eta 1. And I can take out a global phase I delta outside and write my state as cos gamma 0 plus sine gamma ei eta minus delta 1. Let's rename it as omega. So I can kind of write my state psi, which is on the Bloch sphere, as a function of angle gamma and this phase omega, and write it as cos of gamma 0 plus sine of gamma ei omega 1. And why could I do that? Because this is a global phase, that overall phase attached to my psi. And during the start of the lecture, we said that this global phase has no observable effects. So we can kind of ignore it for a computation and write our superposed state psi on a Bloch sphere in terms of gamma and phase vector omega. So our next job is to relate this gamma and omega to our more familiar spherical coordinates, which are theta and phi. So Bloch sphere is you can represent this Bloch sphere in spherical coordinates as well. And spherical coordinates, if you remember from your mathematics, are r, theta, and phi. We choose our Bloch sphere to be a unit sphere, so r is not a variable anymore. This sphere has the radius 1. The variables here for the spherical coordinates are just theta and phi. And theta here is this angle with respect to the z-axis. So this is theta. And the angle phi, if you remember, is nothing but if I take a projection of this vector on my xy plane. So this is my projection. This is my projection of psi. This is my psi vector on xy plane. Then this angle is my angle phi. Okay. So this is my state vector on a spherical coordinate. And remember, using Bloch sphere, we also represented a state vector, but we represented this state vector in terms of not theta and phi, but in terms of new angles gamma and omega. So what we want to do is we want to see what is the relation between gamma and omega, which represent my psi state on a Bloch sphere, is related to these spherical spherical coordinates theta and phi. Okay, and maybe what's helpful here is to check our bases 0 and 1. What are the values for theta and phi for our bases 0 and 1? Okay, and that's probably is going to help us find a relation between gamma, omega, and theta and phi. Okay, let me explain this by an example. Now, in this spherical coordinates, your angle theta, it runs from 0. It is any value between 0 and pi. So starting from here till the negative z-axis, That's the allowed values for angle theta. And your phi, which is this angle on the xy plane, so this angle, it could take any values between 0 and 2 pi. Okay. Now, if I want to check what values of theta and phi my eigenstate 0 takes, let's check 0 state, which is on the z-axis. So on the z-axis, my psi, which is which was 0, cos of gamma plus sine of gamma ei omega 1. Okay, so this is my superposed state, general state on Bloch sphere. Now this general state, if I say that this general state is represented only by 0, I mean that my gamma should be equal to 0 and omega can take any value. Because if I substitute gamma as 0 here, this would be 1 and this entire factor would be 0. So what I'm left with is just with my eigenstate 0. Okay. So my 0 state on Bloch sphere is represented by gamma is equal to 0 and omega can take any value. Similarly, for my eigenbasis 1, my state would be cos of gamma 0 would correspond to, now gamma should be equal to pi by 2 and omega can take any value. Because if gamma is pi by 2, it would mean that this vector here is 0 and what I'm left with here is sine of pi by 2, which is 1. And this is a global phase which won't affect. I can take it as any value. And what I'll get is 1. So my eigenstate 1 on Bloch sphere is represented as gamma can take pi by 2 and 0. And omega can take any value. Now, if I look at these states on my spherical coordinates, this represents 0 and this represents state 1, right? Now, this state 1, which is exactly on the negative z-axis, it corresponds to the theta value. So theta value here, which means pi, theta value would mean pi, and phi can take any value. Let's look back to this picture. So on the spherical coordinates, this negative z-axis would correspond to a theta value of pi here. And since this is the z-axis, there is no projection, phi can take any value, okay? Now, if I check similarities, like if I see the equivalency of gammas and thetas here, it would mean that the relation between gamma, which is representing my state on a Bloch sphere, and theta, which is my spherical coordinate, is nothing but theta by 2, and omega has a direct corresponding to phi. So I can write my state on a Bloch sphere, which I earlier represented as a function of gamma and omega as cos gamma 0 plus ei omega sine gamma 1, as I can rewrite it in terms of thetas and phis, which are now my spherical coordinates, which are much easier for us to do, as cos theta by 2, 0 plus ei phi sine theta by 2. Okay. maybe as an exercise to check if this is clear, let's do it as an exercise. Let's find what would be the relation between gamma and theta for your eigenstate plus. Can you calculate the values of gamma, omega, and theta and phi for your eigenstate plus? Is the question clear?
No, please.
Okay. So what maybe I can do one more example, this particular question, and then assign another question. The question we want to do is, for our eigenstate plus, which is written as 0 plus 1, right? This is my eigenstate for poly spin X. It's written in terms of the eigenbases for poly spin Z as this. What should be the values of gamma and omega, and how they are related to the values of theta and phi? Maybe this I can do as another example and give you one more exercise, a different exercise. So if I look at this equation and compare it with my general state on a Bloch sphere, which was cos of gamma 0 plus exponential I omega sine of gamma 1. Now, if I compare these two equations from here, I can say that gamma should have values pi by 2, pi by 4. Yes, and omega should have value, since I want a plus sign here, maybe 0, yes. Okay, so plus eigenstate on a Bloch sphere corresponds to psi. Gamma is equal to pi by 4. And omega is equal to 0. Which from our earlier relation here would mean that on spherical coordinates, if I choose my theta as, so theta was 2 of gamma, theta as pi by 2 and phi as 0, this would actually correspond to my positive x-axis. And let's check. See, if gamma is pi by 4, then by this relation, my spherical coordinate theta would correspond to 2 gamma, which is pi by 2, and omega and phi are same. So let's check if these values of my spherical coordinate, they actually correspond to the x-axis or not, because this is the eigenstate for your positive spin x. Okay. So on the Bloch sphere, if my theta is pi by 2, which means this is theta. So theta is pi by 2, this angle here. And phi is 0. So phi is this angle, which means I'm actually talking about my z-axis, right? I'm sorry, I'm not able to draw it here, but the vector which corresponds to theta is equal to pi by 2 and phi is equal to 0 on spherical coordinate, it corresponds to this vector in the x direction, right? And that's what information we also get from here, that plus is the state which corresponds to the spin x in positive direction. Is this clear? Or if I'll be happy to repeat if this is like a new topic, and if anyone is not familiar with this or things are not clear here, please don't hesitate to ask again. So maybe we can check. Can you give me values of gamma, omega, and theta and phi for spin down in y direction. Y direction. So I kind of need the values for minus I state. Someone can quickly calculate what should be these values here, corresponding to this direction, this state, minus y, which is minus I. So theta would be
Pi on 4.
yeah, this would be pi by 4. That's right. Gamma would be pi by 4. And omega would be what value? You need negative signs. So omega would be pi, I think, right? Omega would be pi. I pi is -1? Yeah. And then correspondingly, theta and gamma would be pi by 2, and phi would be pi. So it would correspond to minus y direction. I think so. Okay, I think this is it. This is what I wanted to briefly discuss so that you have the basic understanding of what Marina and Ella are going to discuss in their part of the lecture. And the main topic is actually what they are going to talk about. Whatever I talked today was just trying to bring everyone on the same level so that when they discuss more advanced topics, then these concepts which are being used in their lectures everyone is familiar with those topics. I'll give another 2 minutes for anyone to come up with any question, any queries. And I'll also write my email address in the chat window. If someone is not prepared for any questions right now and they have more questions later, I'll be happy to answer them. So before I leave, I'll stay here for another 2-3 minutes and give you those 2-3 minutes to formulate, just go through all the notes and check if you have any questions. So the angle theta is the angle in the spherical coordinate. And when we are representing our state psi in terms of gamma, then it's not necessarily the same angle as angle theta. The relation is that they're related by a half factor. Okay, let me again share and then show it. That's a good question. So my psi state on the Bloch sphere, the general ansatz which I chose was some cos gamma angle, exponential I omega and sine gamma angle. But these gamma and omega angle are not necessarily the same angles which we use for our spherical coordinates. For example, here we show that if I'm representing my plus one eigenstate, which is minus z direction, on a spherical coordinate, if I had to represent a vector in minus z direction, then the angles which I should have chosen was theta as pi and any angle phi. But this state on Bloch sphere, 1 would correspond to gamma as pi by 2, not pi. So the relation between gamma and omega is this. So this is the relation. These are spherical coordinates, and these are my general ansatz which I used to represent any state on the surface of the Bloch sphere. I hope this was clear. So gamma and omega were just ansatz which I chose to represent any state. And then those angles which were my ansatz, I related them to the actual coordinate systems which we use, the spherical coordinate system. What I could have done was, from the starting when I chose the ansat, I could have chosen theta and phi as my ansats. That would have given me the same answer, doesn't matter. But I chose to have a more general angle, which I called as gamma and omega. Yeah. Okay. I think there are no more questions. I'll take it as a positive thing. But please feel free to email me if you have any doubts. You have the notes. And I think Whatever I covered is from notes. I didn't cover anything extra. However, my notes have a little extra information as well, which I didn't cover today. So feel free to go through those notes, and if you have any questions or queries, don't hesitate to email me. And thank you. It was really wonderful being here for the last 2 hours. I enjoyed it a lot, and I hope that you enjoyed it too and learned something new. So bye and take care.